Yeah, so a very good afternoon to all of you. So welcome back to the week 2 of the Introduction to Material Science and Engineering courses. And today we are going to discuss couple of topics, like we'll solve a couple of questions based on these particular topics, and we'll also try to solve if the any doubt which you guys have. Okay, so before I start with this week 2, I hope we all remember last week what we have done. And there was one question by one of you only that fivefold, like in the like, as per the crystallographic reflection theorem, we got to know that only one fold, two fold, three fold, four fold, and six folds are there. Remaining all the folds are not there, and also the five fold is not there. And we were discussing that five fold is not there, but why it is not there? Why it is not able to fill the space? Now, to do that, let's take a one example. We'll take sixfold. Sixfold, one example we can take as a hexagon. I tried to explain last time with the drawing it on the paper, but it was not that I think effective. So what I have made is I made a couple of models using the 3D printing. I made multiple hexagons. So now what we'll do, we'll try to arrange this particular hexagon, and we'll see will they once we repeat this particular unit cell, this particular pattern, will it fill the entire space, or will it leave some of the space blank? So this is one of the hexagon. Let's bring it another one more over here. We can stack them at below also. So we are able to see they are exactly matching with each other. And once I try to repeat this particular pattern, it can go on infinite and without leaving any of the blank space in between. This was what we call that. Okay, this is what why we say that sixfold, which is hexagon, it is following the one of the necessary condition for it to be considered under crystallography is that the it is translational equivalent. It's showing the translation symmetry. Now let's go to the pentagon. So I have a couple of pentagons with me. Let's start with the one. I'll put another over here, just next to it. Trying my best not to trying my best to so that there shouldn't be any gap left in between them. So let me place one below also. Now we can see, no matter how hard I try, I cannot fill this particular space with another pentagon. Okay. Now, still let me go ahead and let's try to do some. We'll try to fit it more. We'll try our best. But now we can see, even though we are trying our maximum, but still the sum of the spaces are left. Okay. So that's why we can see that if we try to repeat the pentagon, which is the indication of the five-fold symmetry, right? They are not going to follow the translation symmetry. Okay, so that's why crystallographic restriction theorem told that this five-fold will not be taken into the account. Not only for the five-fold, if we go for the 7, 8, 9, and so on and so forth, they will follow more or less similar type of spacing. Here, whenever I'm trying to repeat, they are like they are not leaving any space in between them, and they are equally like they can cover the entire space of particular region, whichever is of our interest. But here we are able to see couple of the spaces are left, and that's the reason why this is not been considered under the crystallography. Okay. One another class of material is there which is quasi crystal. Okay. in that it is taken into account. But for our discussion is not on that. So for now we can stop over here. So let me know if we have any particular doubt in this particular section that we discussed just now. Great. Since there is no doubt, we can go ahead with our week 2. In this particular week, the list of the topic that has been covered is Miller indices of the direction and the plane. Second, we discuss about the Weismann law. Then interplanar spacing we discuss between the two plane. Then we discuss about the Bragg's law, and at the end we discuss about the hard packing of the sphere, close packing of the sphere, and we saw the two cases. One can be the hexagon close SCP, and one can be the cubic close pack. So these are the list of the things that we have covered in the class. Before we move ahead and solve the questions, I would like to ask you, do you have any doubt in this particular list of the topic that has been covered in the class? If you have, feel free to mute yourself. So can you explain the Miller indices once again? It will... Okay, yeah, that's great. So we need to understand this Miller indices part. Anything else, guys? Okay, great. So now let's try to... Okay, that's great, Omkar. Again, my recording has stopped. Okay, so let's talk about the Miller indices. How do we calculate the PE? I didn't get. P, I think you are talking about the planar density or packing efficiency, I think. Yeah, I think you are talking about the packing efficiency, right? Yep, I think that will be. Okay, we'll get to that also then. So let's talk about the Miller indices first. So, as per the doubt by Omkar, let's have a clarification on the Miller indices. Right. So Miller indices, it can be for the both. Like it used to indicate the family of the plane. It used to indicate the plane and also the direction. It can represent the single direction. It can also represent the plane of direction, family of direction. It can indicate only the single plane, and it can also do the family of plane. Okay. At the end, what we write, if we are talking about the planes, and in the second case direction, for the plane we use the symbol like this. For the single plane. For the family of plane we use the symbol like this. For the direction we are using the symbol like this. Single direction. For the family of direction we'll use the symbol like this. This is must. We have to remember it no matter what. Some of the questions, for example, let's say gate question, if we talk about, they can confuse us only by this information itself. Okay, they can tell that, okay, tell me the options which represent the 111 plane, and the option will be given like this. And then it will be like this. They'll say, okay, tell me which one will represent the family of plane among this family of plane of 111. So we see that, okay, all of them are similar. All of them have the same number, but they differ in some way. Okay, so this is how they how we notate, how we can give the symbol to them. Okay, now let's try to find that how we can find the family of directions. Sorry, how we can indicate a particular direction and how we can indicate the plane. Before that, let's try to solve this particular question. In value indices of a direction, which type of brackets are used to denote its denoted direction? A, B, C, D. A direction. Very good. That's right. Everyone has answered. The right answer is option C. Okay. And if I talk about the family of direction, in that case, what will be the answer? Can anyone tell? Instead of a direction, if it would be family of direction. Yeah, great. So this will represent the family of direction. Now let's go to the question. Question number 2. Here we will try to find the Miller indices. Okay. As the question by the Omkar, we have to clarify. Slowly we will take the Miller indices part now. There are the steps. Our question is that we have to find the Miller indices of a particular direction. Direction is given to us. There are the couple of steps we have to follow. First of all, we are doing for the direction right now. So the steps are, we have to choose the origin at one point. We can see this direction is made up of, if I start one point over here and another point end over here. Choose your origin at one of the point, either this or this. For the convenient, I will choose the origin over here. Now, second step, choose the coordinate system. Coordinate system means that we have to choose the where will be the A direction, B direction, and C will be, right? Okay, so someone has already answered. Yeah. So 1 minus 2 and 1. So Githu's answer is, the answer will be the 1, 2 bar 1. Great. Okay, let's see. So from here now we have to define the coordinate system. Okay. So this will be, let's say this is x, this will be the y, and the z direction will be above. We just have to make sure that if we do a cross product from the x to y or a to b, it should point toward the z. Okay, don't take z like this suddenly. Okay, it should follow the rule. Now from this point I have to go to this particular point. It is at the face center of this particular plane. See, we define the origin, done. We choose the coordinate system. Now we have to find the coordinate of the other point, of this particular point. So how we can do? In the x direction, by how much amount I have to go? If we see x direction, we have to go only by the a by 2, considering this entire to be the a. Now in the y direction, how much we have to go is this is the y direction. We have to travel throughout this much to this particular plane. It will be how much? The entire distance is b. So we have to travel by the b. And the z direction, we have to travel by the amount of, this is entire, if it is c, then we have to travel by the amount c by 2. So it will be CO2. So if I start from origin, if I travel in the x direction by a by 2, in the y direction in the negative way, sorry, it should be minus b because I am traveling in the negative direction. It will be minus of b. And then for the c, I have to go up by the c by 2. Okay, in the third direction. So what I will get? The coordinate point of p, we finally got the coordinate point of the next, this particular point, let's say this is the origin and this is point A. So point A, I have got the coordinate of the other point. Now the last one, we have to reduce it to the smallest integer. So first of all, what we'll do, we got these particular points. What we'll do, we'll remove A, B and C. 1 by 2 minus 1 and again 1 by 2. So now this three number which we have got, we have to convert it to the smallest, reduce it to the smallest integer. We'll multiply entire by 2, it will be 1 minus of 2 and 1. What we can do last is that we have to put them in the square bracket. Still it's not done yet. What we have to do next? This minus 2 we have to write it as a 2 bar. So in the crystallography, the negative indices will be treated as a bar at the top. So the answer which was given by the Gitu, 1, 2 bar and 1 is right. Okay. So let me know if there is any doubt in this particular steps which we have followed. I will repeat again once. We choose the origin. We define the coordinate system. Okay. Then after that we found the coordinate of the other point, and then after that just couple of steps we remove the A, B and C, and then from there we just reduce it to the nearest whatever will be the smallest integer, and from there we just put it in the bracket and use the bar symbol to represent the negative values. Clear? Any doubt, let me know. If not, we can move to the next part. Clear? That's great. One important point to note down: while defining for the direction, we choose origin at the one of the direction point, which will be on the direction. Okay, but for the plane, we have to make sure that our plane origin should not lie onto the plane. Okay, these are the things which we have to remember. Okay, any comments? No, fine. So that's what the thing, and now let's go to the next question. Question number 3. Again, we have to find the method indices of this particular plane. How about all of us give a try? It's not difficult, it's very easy question. Right? What we have to do, first we'll choose the origin, then we choose the coordinate system, then again after that we'll go with the coordinate of the other point, then we'll reduce it to the smallest integer, and at the end we'll put the square bracket. Okay, so let's define our origin at one of the point. I will choose this one. Then we'll define the coordinate system. Coordinate system I will define like, let's say this is my x direction, this is y, and then this one will be z. It is at the center, right? This point is at the center of the body center of this particular cube. So the point will be at the, if this entire thing is, this is A, and this is A. Or let's say we can take it different also, A, B and C. So this point will be at the A by 2, B by 2 and C by 2. Right? But now taking this as origin, this point will be not A by 2, right? It will be minus of A by 2, minus of B by 2 and minus of C by 2. Or in the C direction it's a plus, because C still it's a positive point. C is still positive. So overall what we can see is that A is negative, B direction is negative, but C direction is positive. So we got minus 1 by 2, minus 1 by 2 and 1 by 2. Our first 3 part has done. We choose the origin, we define the coordinate system, where the coordinates of the other point also we have got, and now all we have to do is reduce to the smallest integer. The denominator is 2, so we'll multiply all of them by 2. What we'll get? Minus 1 and 1. So now what we can see that once we put it in the bracket, 1 1 1, here it will be bar, here it will be bar. Clear? So this is the direction of the particular, this is the Miller indices of this particular direction. Okay. 1 bar, 1 bar, 1. That's right. So Swarangi has got the answer. So the right answer is 1 bar, 1 bar, and 1. Very good. So with that, we have solved the question number 3. If there is any doubt in these two questions, they were more or less similar type. Only the coordinate of the last point has changed. Okay. If the direction instead of this, if the direction would be this, then it will be easily we can guess this direction is opposite of this particular direction. So it will be what? It will be 1, 1, and 1 bar. Just opposite of this. Right. Great. Okay, let's go ahead. Let's try to solve the next question. Question number 4. Question says, all face diagonal of the cube is given by. Face diagonals of the cubes, first of all, they are the directions. Next part is that all of them. So it means that we are not talking about the single, we are talking about the group. We are talking about the entire plane. Right. So here we can say we are talking about the family of direction. I think I used the word by mistake plane, but it's a family of directions. And how we represent the family of direction is with this. This will be for the family of plane. So Abhimanyu has answered the option is A. That's right. Because face diagonal will be this 1, 1, 1. These are the body diagonals. They correspond to the body diagonal. Just now we have saw in our last question that this particular directions, it was going from the 0, 0, 0 origin to the body center of the particular cube or any crystal system you can say, and it has the direction of 1 bar, 1 bar, 1. Okay, so here we can say that this will correspond to the body diagonal. This too will correspond to the face. But again, we are talking about the directions. So we'll remove this. The right answer is option A. So as when you told us that the right answer is A, it's correct. Okay. So with that, we have solved this question number 4. If there is any doubt till now, let me know, guys. If not, we can move ahead to the next part, question number 5. This is our question. How many unique directions does the family this represent in the cubic crystal? 6. Okay, everyone is saying answer C. Very good. It can be, so let's type those directions. It contain 1, 0, 0. Okay, sorry. I should write the square bracket. We are talking for the directions. 0, 1, 0. 0, 0, 1. And they are correspondingly negative of them. 1 bar, 0, 0. 0, 1 bar, 0. And 0, 0, 1 bar. Right. Very good. The right answer is 6 total. If I change from 1, 0, 0, question I change from 1, 0, 0 and I make it 1, 1, 0, or I make it 1, 1, 1. What will be the value in that case? How many unique directions they are representing? Here we can say it's representing overall 6 directions. What about the second case? Mm, any idea, guys? Any, about 111? Sorry, 110. 4. Uh, it will be on one of the faces. It will be 4. Let's take a cube. Let's take a cube. And for a time being, let's say my focus is on this particular plane. If I talk about this particular face directions, then it can go like this. 1. It can go in the opposite of this also, right? 2. It can go like this. 3. Opposite of this also. 4. So one face we got 4. In one face we got total of 4 of this particular direction. This face and this face are equivalent, so no need to take that into account. This face and this face are equivalent. Which are the next face? We talk about the side one. Now we have to talk about the below one also. That will also have 4. This, this, and so on, this direction. How about this vertical face, which is this one? I hope we are able to get this. So we have total of 3 unique faces over here. In this particular 6 faces of the cube, we have 3 unique faces, and each of them is having the 4 of these particular directions, right? So the right answer will be 4 multiplied by 3, that is 12. So 110 will have a 12 of this, and 111 is 8, right? So this is how we have solved this question. So we'll remember this, because 110 has 6, 111 has 12, 111 1006, yeah. Okay, so this thing you must remember. It is very useful when you solve the questions based upon the X-ray diffraction. Okay, if there is any doubt in this particular part, let me know. If not, let's move ahead to the next part, question number 6. Question 1. When determining Miller indices, the coordinate must be reduced to the dash integer. Largest, can it be? Reduced to the dash integer. Very good, Omkar, that's the smallest integer. Yeah, yes, Ravenu, that's right. So it's a smallest integer. Great. Let's go to the next one. The notation this is used to represent a dash of equivalent direction. This particular notation, great. It's a family of. It doesn't represent a single. It is the entire family will come with it. Now the last part, little tricky. In tetragonal crystal system, 110 family include how many directions along the dash axis? Include only direction along the. In tetragonal crystal system, this particular family. So first of all, this represents the direction. 100 we are talking about. Very good. That's the x-axis. Yeah, only along the x-axis. That's good. Okay, let's go to the next part, question number 7. If there is any doubt in this one, let me know. Okay. Finally, this question we can easily solve. Question number 7. UVW square bracket HKL uh, round bracket. One will going to match with the when you told that A is with the D. What about the second one, HKL in the round bracket A, B, and C. Okay, I think it was some network lag from my side. So the second one is A. It's a single plane. Great. Third one, HKL. Okay, yeah. When you told that, it's a option B, family of plane. And UVW at the end, we got that it's a family of direction. Great. So the right answer is D, A, B, and C. Great. Okay, now we can move ahead to the next part, question number 8. First one. The origin should always be placed on the plane while determining its Miller indices. Plane we are talking about. Whether it's a true or a false. False, that's right. Now, instead of plane, if I write direction, in that case, what will be the answer? Answer will be true. Great, guys. Now let's move ahead to the next part, question number B. The reciprocal of an intercept are used to determine the Miller indices of a plane. We need to do reciprocal in the plane. Yeah, that's right. Yeah, it's a true only. Do we need to do reciprocal while determining the indices for the direction? False. Great. Yeah. Good. So we have solved A and B. Now let's go ahead to the next one, option C. In the cubic crystal system, this represent all 6 symmetrical related faces. True. This one is representing the all of the faces, right? Front, back, and sides and all those are there. So these are the family of the faces. Yeah. Let's go to the next one, option D. A negative Miller indices is represented with a negative sign before the number. Example, -100. False. We represented it like 1 bar. Yeah, that's right, Swarangi. The last one. In a tetragonal system, the horizontal and the vertical faces belong to the same family of the plane. Now, we need to discuss about the tetragonal crystal system. Now, let's take the two cases. The case 1, horizontal faces. We know it's A equal to B, not equal to C in a tetragonal system. Yeah, most of you has told that it's a false. Very good. The answer is false only. Let's see why it is. So if I take this particular square, this is A this is P, and this is C. Since A is equal to B and the angle is 90 degree, we can see that it's more or less like a square. The base will be, this entire thing will be the square. If I rotate it by 90 degree, it will satisfy the symmetry, like after 90 degree rotation, it will be equivalent with with this. But what about this particular thing? Now let's talk about the vertical phases. If I try to rotate this by 90 degree, this is C and this is, let's say, A, and they are not equal. If I try to rotate this by 90 degree, it will not happen. It will be something like this. But if I rotate by 180 degree, then it will be coincide. So their symmetry are different. The horizontal one has a different symmetry compared to the vertical one, right? So that's why the tetragonal system, the horizontal and the vertical faces belong to the same family. They do not belong to the same family, right? We need to separate them. The family will be this one, and this one will be clubbed together, and the vertical one will be different. While in the cube, all of them were equal, because A was equal to B and equal to C. So that this is how we classify things. A couple of questions we'll see more on this particular part, because this is quite confusing, and like lot of questions can be made on this particular things. So this is what the question number 8 was. Let me know if do you have any doubt in this particular part, question number 8. Okay, great. Since there is no doubt, let's move ahead to the next part, question number 9. According to the Weierstrass law, if a direction lie in a plane HKL, what must be the true? Option B, right? Very good. So if any direction, if there is any plane is there, the plane which is represented by H, K, L, and any direction is there, U, V, W. And if it is lying on the plane, that means that it will satisfy this particular condition, and U into H plus V into K plus W into L will be equal to 0. Not only lying onto the plane, let's say if this is my plane, this paper is a plane, and initially my direction was onto the plane. Now my direction is shifting. It went up. The property of vector is that we can make it parallelly, it can move down. So it is also lying onto the plane. Either it should be lie onto the plane, or it should be parallel to the plane. In both the cases, this particular condition is going to satisfy. Okay, so HU plus KV plus LW, this is a Weierstrass law which says, and we are going to use this particular thing to solve a couple of numericals. Okay, let's try to solve the question number 10. Imagine you are given a crystal with a unit cell. Find the common direction between this. Let's say we are talking about the cubic crystal right now. Even though things are not going to be different, we have to find the common direction between 1, 0, 0 and 0, 1, 0. Let's draw a cube. Guys, feel free to answer in the chat box if you have already got the answer. Let's say this is my x direction, which is A, this is P, and this is C. So we are talking about the plane 1, 0, 0. plane 1 0 0, it means that it is going to cut the x-axis at 1, and 0 0 means that it is not going to cut the y-axis, and neither it will cut the z-axis. So we are talking about this particular plane. Let's go to the next plane. 0 1 0. It means that it is not going to cut the x-axis. It will cut the y-axis at 1, and z-axis again it's not going to cut. So what we will get? It is this particular plane. What we have to find? Find the common direction. This is our question. This is the plane number 1, this is the plane number 2, and we have to find the common direction between them, and the common direction is nothing, it is this one. Right? This direction is common in both of them. Right? So now what we can say here, what is this particular, we have to find the overall, at the end we have to find this particular direction. What is this particular direction? Any idea, guys? Zero zero zero. Anything else? Yeah. Abhimanyu, not 0 0 0. Swarangi is telling the Z. That's right. So it is going along the Z direction, right? So if I have to find this particular direction, I will take origin at one of the point. Another point I will try to find. What I'll get, let's say if I am taking this particular as a direction, origin, I have to select my coordinate system now. This will be the X, this will be the Y, and this will be the Z. So from here, where I am moving only along the Z, that too by the amount of, if this is A, B and C, I am moving by the amount of C. In remaining direction, X and Y I am moving 0 0. So what I will get? 0 0 1. So with that, I can put it in the square bracket. Right. This two plane, what we have got the direction is 0 0 1. Clear till now? Any doubt in this particular part? If any doubt is there, let me know, because next question will be a little bit more complicated. It was the easiest one, right? Last part once more. Very good. If you have any doubt now, guys, you should tell me, because this is a doubt solving session. So we got that this is a common direction. So I will highlight here. This is my common direction which I have to find. Remember how we perform in the question number 2 and 3? What was our step to find the Miller indices of a direction? Choose the origin, choose the coordinate system, choose the coordinate of the other point, and then reduce to the smallest integer, and then put it in the square bracket. We'll follow the same thing. We'll first choose the origin. Let's say this is my origin. Now I have to choose the coordinate system. Coordinate system will be along, let's say this is my x direction, this is y direction, and this is z direction. So now I have to choose what is the coordinate of this particular point considering this coordinate system. In the x direction I am moving by 0. Y direction again 0. In the z direction it is by the amount of c. Or if it is cubic, a equal to b equal to c, then all of them we can say that c will be equal to a. So this is my coordinate of the point 0 0. We can remove this a, b and c part. What we will get? 0 0 1. Right. So at the end we can put it in the square bracket. So this is the direction which we have got. Okay. We follow the step: origin, coordinate system, coordinate of the other point, then reduce it to the smallest integer. It was already smallest, so no need to do. Okay, and then the square bracket. So these are the list of the steps that we have followed and we have got it. Clear? That's great. Okay, so this question number 10 is clear. Now let's go to the next question, question number 11. Guys, before we start, this plane is unique in a way that it is lying, this direction is a unique in a way that it is lying on the plane 1 as well as plane 2. We remember we followed we know one law, Weismann law. That also we can do over here. Okay, okay, let's go ahead. Now, suppose you are given a two plane, plane is 1, 2, 3, 1 bar, 1, 1. What is the common direction between them? Previously, we were able to draw at least. Now we have 1, 2, and 3. Okay, even though one can draw, but it will be little complicated to solve it. So, all we will do is, we are given a two plane. Okay, let's say plane 1, plane 2. Let's say this plane is 1, 2, 3. This plane is 1 bar, 1, 1. This is the common direction between them which we have to find, and let's tell that this direction is UVW. Now, instead of geometrical, the way we have drawn last time, instead of visualizing in that way, we can apply the Weismann law. Weismann law says that HU plus KV plus LW will be equal to 0. Now apply that. Let's apply that. This is our HKL. So we'll apply first with this and then we'll apply with this. Because since this direction is common to both of them, so it will satisfy both of them. So in this case, we will get 1U plus 2V plus 3W. It will be equal to 0. Now we got U plus 2V plus 3W is equals to 0. This is our equation 1. Now let's apply again over here. What we will get? minus 1U plus 1V plus 1W is equals to 0. So here we got minus of U plus V plus W is equal to 0. This is our equation 2. Okay. So now we have to find U, V and W from this. Okay, let's do one thing. Let's add both of them. What we will get? If we add both of them, U and minus U will be cancelled out with each other, and what we will get? 3 times of V plus 4 times of W will be equal to 0. So we got V is equals to the 4 over 3 minus of 4 over 3 over W. So we got the V in terms of W. Let's substitute this back to the equation number 2. We can find the value of U now in terms of W. So equation 2 was minus of U plus of V plus of W is equals to 0. What we have got from here? Minus of U plus V we can substitute minus of 4 over 3. We can easily solve this. Let's shift U to that side. Minus of U will become plus of U. And from here we will get minus of 4 over 3 minus 1. Once we solve it, minus of W over 3 we will get. What we have to find? We need to find U, V and W. Let's substitute whatever we have got. Let's substitute whatever we have got. We have got U as minus of W over 3, V as minus of 4 over 3W and W as a W itself. The common factor they have is a W. We have to reduce it to the smallest what is possible integer, right? So what we'll do, we'll remove all the W over here. So what we will get? Minus 1 over 3 minus of 4 over 3 and then 1. Again we can reduce it further. We'll multiply all of them with the 3. So what we will get? Minus of 1, minus of 4 and then 3. We can represent it like 1, 4, 3 bar. Okay, so this is how we have to do. Once we have two plane, we can apply the Poisson law. Okay. Yeah. So once we have a two plane, we can apply the Poisson law and we can find two of them in terms of the second one. So for example, here we found U and we found V in terms of W and we substitute all of them over here. We remove the W as a common factor among them and 3 we just multiply with them. Okay, so and remaining thing is just going to the smallest integer part, and this is how we have solved and we have got the answer. So the places where you will find that okay, this is very difficult to visualize, in that case you can apply the Poisson. Mathematically you can solve it. Okay, you can treat this one as your your own assignment. You can tell, like you can find the H, K and L, sorry, you can find the U, V and W the way we found 0, 0, 1. You can find U, V, W in terms of using this particular question itself, using the Poisson law, and verify whether you are getting the same answer or not. Okay, great. Let's go to the next question. Question number, if this is clear, we can go to the next part. Question number 12. According to the Bragg interpretation, a diffracted X-ray beam can be viewed as a transmitted through a material, specular reflection from a crystal lattice plane, absorption by the lattice, scattered in all the random directions. Very good, that's right. The right answer is option B. So if I see a plane, it's like a reflection from the plane. If I see a plane, X-ray is coming, it will be diffracted. Yes, Swarangi and Omkar, that's great. So it will be like a, we can say it will be like a mirror, specularly reflected. So with that we have got the answer B to be the right answer. Let's go to the next part, question number 13. Sir, I'm in a NPTEL video. Okay, sir. Yeah, so what we have to do is, what is the packing efficiency of the densest possible sphere packing in the 3 dimension? What is the packing efficiency of the densest possible spheres packing in the 3 dimensions? So we are talking about the 3 dimensions. Okay, yeah, that's great. The right answer is C. Can anyone tell me which one it is? Okay, you guys told that it's a C. Is it simple cubic, body centered cubic, face centered cubic? Very good. Abhimanyu and Gitu has told that the right answer is the FCC. This is 74%. What about BCC? How much it will be? Very good. That's a 68. And the simple cubic is will be the, it will be having the smallest one. What will be the value? 52, right? That's great. One more point. Not only FCP, face centered cubic, also the HCP, hexagonal close pack, they also have the same 74. Okay, this we will remember. Now forget about these things that we have discussed just now. Like we will remember this. I mean, don't forget. For a time being, just for the questions, I am going to modify. Instead of 3 dimensions, I am going to write 2 dimensions. What will be the right answer in that case? What is the packing efficiency of the densest possible sphere packing in the 2 dimension? This is something which we which Professor Rajesh Prasad has solved in this particular week. Okay, so it will, the right answer here will be the, first of all, let's see the what the question mean in two dimension, how we can pack it. This is the sphere. If I try to pack like this, this is case 1. This is a case 2. What do you think, in which case 1 or case 2, which one will be the more denser? Square packing or hexagonal packing? Case 1 or case 2, which one is more densely packed? Hexagonal packing, right? Very good. So if I just take their centers and join them, they will make the hexagonal packing. Very good, Omkar, that's right. So now we got the hexagon. This is known as the hexagonal packing. So now if we talk about the packing efficiency, if I talk about the packing efficiency here, what I will get is that at the numerator I can put the area occupied by the atoms in this particular plane. So we can say that it will be this area. Divided by the area of the particular. For a timing we have the hexagon, area of the hexagon we can write. This is known as the packing efficiency. Okay. Omkar has told that the right answer is 90.7, and that's right. So this is what we have got. So once we do this is very easy, geometrical mathematics we have to do, and we'll get the answer to be the 90.7. Okay. I usually saw a couple of my friends who get confused between the packing efficiency and the planar density. So we'll clarify here itself. The bottom will remain as it is. Area of the hexagon or area of the particular plane, if they are talking about the certain plane, or if we are talking about the hexagon, above will be the number of atoms. Here, when we are talking about the packing efficiency, we were telling that it will be the area of the atom which is occupied. Here we have to say that the number of atom that is there effectively. So here one atom, they are going to contribute certain extent, like this angle is 120 degree. So this will contribute to the 1/3, because remaining 120 will go to the different hexagon. So effectively 3 of them will make a 360 degree of angle, and they will contribute entirely 1, and this 3 will contribute 1. So effectively we will get here as a 3 number of atom, effective number of atom will be 3. So this is the difference. We have to remember that the planar packing efficiency and the planar density, they will differ in a numerator way, not in the denominator way. Good. So we have got that 74 will be the for the 3 dimension, and 90.7 will be for the 2 dimensional of the densest possible sphere packing. Any doubt in this part, guys? If not, let's move ahead to the next one, question number 14. The question say, what is the coordination number in 2-dimensional hexagonal close pack structure? We talk about the close pack structure, hexagonal close pack structure. What is the coordination number? Omkar, answer is 6. Abhimanyu, answer is 6. This is right, guys. The answer is 6. Coordination number is defined by the how many number of atom that is touching the particular atom. So if this is our atom which we are selecting right now, we can say that it is shared by the 1, 2, 3, 4, 5 and 6, right? it is stretching this number of atoms. So total coordination number will be the 6. In the 2 dimension of the hexagon closed pack we talk about. Now tell me, we talk about the face centered cubic. We should also know about the body centered cubic, simple cubic, their coordination number. What will be the coordination number in the FCC, face centered cubic? Face centered cubic will be the 12, right? So one atom in the face centered cubic will be shared with the 12 atoms. Body centered cubic, there is one atom as the body center of the body and 8 of them at the corners, right? So the right answer here will be the 8, and in the simple cubic it will be the 6. Yeah, that's right, Swarangi. Gitu has answered 8, and here we got the simple cubic for the 6. So both of you are right. So this is also we will remember. Okay. So we'll also remember this planar density. Sorry, this we'll also remember the packing fractions, and also this coordination number. Okay. So along with the 2 dimension, we are just taking into account the 3 dimension just because, like, I thought it will be easy for us to remember in this particular way. Okay, any doubt? Let me know. If not, let's move to the next part, question number 15. Which of the following is not true about metallic bonding? Which of the following is not true about the metallic bonding? First, it is directional. It allows the atom to pack closely. It leads to the formation of the as many bond. It contributes to the stability of the atom or stability of the metal. The right answer is, yeah, this one. So this is incorrect, and so this is correct also. Okay, so it's a directional bond. No, it's a metallic bonds are not directional. Okay, metallic bonds are not directional. They can form as many. So one sphere, one atom can be surrounded with as many it can. For example, in the FCC 12, it is surrounded with the 12 of them. So whatever the maximum that is possible for that particular structure, it will follow that. Okay, it will try to make as many bonds as possible. Okay, it contributes to the stability of the metal and it allow atom to be closely packed. This is also true. So here the only incorrect one is the directional, and metallic bonds are not directional bonds. Okay. Okay guys, let's go ahead. Let's go to the next part, question number 16. First one, packing efficiency. Among all of this, which one will be the right answer? Abhimanyu told that it's E, Swarangi E. Okay, I think it will be it only then. Fraction of the total volume occupied by the sphere. This is the packing efficiency. That's right. Casing number. Second will be the C. Maximum number of sphere a given sphere is stretching. That's right. So our C is done. E is done. Hexagonal close pack. Which stacking it will follow? 3 is D. This is right. This is nice, guys. Option D. So HCP stacking, if we talk about, HCP and FCC. HCP will follow ABAB and FCC will follow ABC. Okay, sorry, you guys have also answered the fourth one. For the cubic close pack, the answer will be the, yeah, that's right, option B. And for the metallic bondings are this is done, non-directional bonding that allow the dense packing, right? Very good. The right answer is A over here. So E, C, D, B, and A. Any doubt in that? Any doubt in this particular question? Let me know. If not, let's move to the next part, question number 17. The first question: in a one-dimensional closed packing, each sphere is in contact with the four other spheres. One-dimensional. The focus should be on the one dimension. False. Okay, everyone has told the answer. It's a false. So instead of four, how many it will be? What do you think? What will be the answer instead of four? If I want to make it, yeah, that's right, true. It will be the two. So if I try to do a close packing in one dimension, one atom will be surrounded with only two atoms. Okay, dimensionality restrictions. Let's go to the next part. B. The packing efficiency of a two-dimensional hexagonal structure is 90.7. True, right. Great. Option C. Sorry, third question. A square packed structure in a two dimensions has the highest packing efficiency than a hexagonal closed structure. The square pack is having more than the hexagon in two dimensions. False. You guys can roughly somewhere maybe after this particular class you can find what will the packing efficiency of the square and what is the packing efficiency of the hexagon. Hexagon we have already got, but how to calculate that geometry part, try to do by yourself. Okay, that is it's very basic mathematics. Let's go to the last part. In a cubic closed structure, in a closed packed structure, atom can be placed at both B and C positions simultaneously. Okay, this question is in a way I should have removed this question. Actually, I not defined the B and C. I should have put one figure over here so that I can define the B and C. Okay, so we'll remove this question. Maybe I will try to include it in the next part. And not frame it properly questions. Okay. Okay, we can neglect this particular questions, guys. Let's not discuss about it. I should have placed one figure where it should say about the position A, B, and C, which I'm talking about. Let's go to the next part. Question number 18. By the way, I think most of you have already answered. The answer is false. It means that we all are following the lecture. So we all know which B and which C position we are talking about. That's right. That's good. Let's go to the next part, question number 18. All the member of symmetry related family of directions in a tetragonal unit cells are. Okay. Family of directions we are talking about. Family of directions. Okay, I think there is some mistake over here. It will be this. Okay. So now all the member of the symmetry related family of directions in a tetragonal unit cell. The question is 1, 0, 0. Let's draw a tetragonal unit cell. So let's instead of family, let's take one itself, this itself, and let's try to draw its where this particular direction will lie. The direction, let's say this is the origin, so this direction is nothing but it's going along the x direction. So this is the direction we are talking about. Okay. So this direction, we have total this also and we have this also. So along this particular direction we can see, and along this particular direction we have same symmetry. A and B are equivalent, but C is not equivalent in a tetragonal, right? But in the cubic we know that all three are equivalent. So which and all the family can follow over here? We are talking about the 1 0 0. So it will be this itself, its opposite, this one, and its opposite. So what we can write? The A will be the 1 0 0. Sorry, again I use this round bracket. Then it will be the B, we can say that it will be 0 1 0, and their opposite 1 bar 0 0, and then 0 1 bar 0. Any option like this? Yeah, option C is the right answer over here. If instead of this, if instead of asking about this, if I wrote about this particular direction, then in that case the right answer will be, in that case how many directions we can get? Only one, and the opposite of this 0 0 1 and 0 0 1 bar. So what will be the right answer in that case? It will be the B. In our present question, we got the right answer to be the C. Okay. Is it clear, guys? Let me know if there is any doubt in this. Most of us are facing, I think, a problem over here, maybe. If yes, please let me know. Okay, since there is a problem, right? Great. It's good that we are able to tell. Let's try to solve. Let's try to understand that concept then. Perfect. Let's try. Let's talk about the cube. Here, let's say this is my direction A, B, and C. Here, all of them we know that A is what? 1 0 0, B is 0 1 0, C is 0 0 1. So if I write a family 1 0 0, here what will come? All of them are equivalent with each other. Equivalent in a way, what I mean is that if I'm rotating, let's say, see, this is the C axis. It is a vector only. I can write C axis like this itself. This also is a C. This vector this vector I just place it, I brought it over here. No problem. If I rotate cube along this particular axis, along this particular direction by 90 degree, it will brought into the self coincidence. Along A also, if I bring A from here over here and I try to rotate a cube by 90 degree, I will get the same. It is equivalent. Along B also, if I bring B over here and I try to rotate this cube along the B direction by 90 degree, again I will get the same. So direction A, B and C are symmetry equivalent. In cube. So what we can say that 1 0 0 will have all of these particular directions. If I write only one direction, one of the plane, family with the one of this notation, it will come all of them. It will come 1 0 0, 0 1 0, 0 0 1, and so they are negative also, 1 bar 0 0, 0 1 bar 0, 0 0 1 bar. So this is the with the cube. Till now we have got that all the directions here are equivalent with each other. All the these three direction 100, 010 and 001. So symmetry equivalent, please repeat once more. That's good. Now let's take a something cube. Do I have anything cube? Okay, what we can say that, let's take this particular cube and along C direction. See, this is the axis. I brought it over here and I try to rotate this cube. Okay, so what I can do currently is that I can take one page and I can cut it. It's not perfect cube, but still we'll try. Okay, so let's say this is the top face. Top face means this one. This and this are equivalent with each other. This is, let's say, capital A, capital B, C and D. This is also, let's say, A, B, C and D. If I bought this particular, if I'm trying to rotate this particular thing by 90 degree, this is a square, I will rotate, I will get a square by 90 degree. Again, I'm getting the same. So symmetry along C axis is preserved by 90 degree, right? Now what about the A direction? If I take about the A direction, if I try to rotate the cube along this particular direction and considering this particular face to be this face itself, okay, now what I will get, again if I rotate by 90 degree, I'll get the cube only. I'll get the same face. So if you take a cube, you will rotate, you will get the same face. Okay, along this also, if I try to rotate along this particular axis by 90 degree, I will get the same shape, right? Symmetry mean that if we are doing some operation, initial and final, if they are same, then we can say that along that particular operation, the shape or the object is equivalent. Here I am rotating by 90 degree. It means that the symmetry is preserved over here by 90 degree. Okay, if take a cube, rotate by 90 degree, you will get a cube itself and no phases will be changed. See here, this is the rectangle. Consider that this entire thing is a plane. Rotate by 90 degree. Did we got the same thing what we got before? No. If I rotate by 180 degree, then we got. So what we can say, the initial object which was this, it is symmetry equivalent to the final this one. By what? 180 degree. Okay. Now, top face, if I try to rotate this top face, if I try to rotate by 90 degree, it is happening by 90 degree. This happening by 90 degree. The front face also rotate by 90 degree, you will get the symmetry equivalent. So all the directions we can say in that way. That's what I am saying, that all the directions are symmetry equivalent. So all of them will correspond to only one family. Okay. So this is what I mean. Now same thing. We talk about the square. We talk about the square. Now in tetragonal, let's draw a tetragonal. Here we know that they are equal, but this differ. So along the C axis, along this particular axis, this particular phases, along this particular axis, we can say that these particular phases are stretched. From the cube, if I stretch along this particular direction, what I will get is this. Below one is following the symmetry of the previous one. What it is? 90 degree. If you rotate by 90 degree, I'll be symmetrically equivalent. But what about this particular direction? See, if I rotate about this particular direction, vertical direction, vertically if I see, I'll see, okay, only a square is there. If I rotate about this, 90 degree rotation it is following. So along C direction, if I'm C axis, this is along C axis, if I'm rotating, it is following the 90 degree rotation. Now if I try to rotate by, let's say this is the B direction, and along B direction I'm trying to rotate. First of all, what is there along the B? The phase is like this. By how much amount I have to rotate to make it symmetrically equivalent? Can someone tell me? If I have to rotate it and I have to make sure that the rectangle should come rectangle, by how many degree I should rotate? It's right, Omkar, it's a 180 degree, right? So this was along the B direction. So the C direction and B directions, they are symmetrically, they are not equivalent. They are following the two different symmetry, right? They are symmetrically not equivalent, so they will not correspond to the one family. 180 degree rotation, right? That's great. So they will not correspond to the one family. This B will tell that who else is making the same family like me. For example, now let's talk about this particular phase. The back phase. Any idea whether it's making the square or it's making a rectangle? The back face of the tetragonal. It's making a rectangle. The side face and the back face, they are making a rectangle. Only the base, this face and this face, okay, only the horizontal faces, they are making the square. Remaining two of them are making a rectangle. So this is where both are rectangle, right? So B, along with B, C is the one which is making the family, because they both are making the rectangle and they both are following the same symmetry. They both are telling that by 180 degree rotation we will be symmetrically equivalent. Only base and the top is square. That's right. Great. So the base is following the 90 degree. Vertical direction, if we say, they are following the 180 degree. So C axis is following the 90 degree rotation. If I rotate about the C axis, it will be symmetrically equivalent. But if I rotate about the B and A axis, they will tell that we want 180 degree of rotation, then only we will be symmetrically equivalent. So they are not in the same family. They belong to the two different family. Okay. So C direction will differ from A and B direction in this way. And this is why, now let's get back to our question. We told that C is different from A and B symmetrically. But A and B are following the same symmetry. They are telling that we are symmetrically equivalent, even though we are 180, but we are symmetrically equivalent. So we'll write the about A. A is what? 1, 0, 0. Opposite to the A is minus A, that is also 1 bar 0, 0. B is 0, 1, 0. Opposite of B is 0, 1 bar 0. They will form one family. Their family will be in a way that about this particular direction, if we rotate by 180 degree, they will be symmetrically equivalent. C will say that my symmetry is different, 90 degree of rotation, 0, 0, 1, 0, 1, 1, 0, 0, 1 bar. So they will be 90 degree of rotation. So it will make a different family. So whenever the question come to you in front of you that it is say about this and it say about this corresponding to the tetragonal, remember they are different. They contain different number of family. 100 will contain the family of 4 direction. 001 will contain the family of 2 directions. And those 4 and 2 direction we are able to see. Let me know Any question in this part? Is it clear or any confusion is there? Please let me know. We can have further discussion on this. All clear, sir. Omkar got clear. Yeah. Anyone else? Any doubt? Okay, great. If there is any doubt, you can always write in the chat box. We'll again come back to this problem. Okay. Question number 18 is done. Question number 19. Things were a little difficult right now. Okay, everyone understood. That's great. Now here. 19. Work out the common direction between the 111 and 001 in a triclinic unit cell. The question is this. We have to find the common direction between this and this. Using the triclinic in a triclinic unit cell. Remember we talked about one Weismann law where it went. Right? When we talk about this law, we not specify whether its law is applicable for which unit cell, which crystal system. We not specify. The reason is that it's valid for all crystal system. It doesn't matter whether it's a cube, tetragonal, orthorhombic, or triclinic or monoclinic. This will be valid for all the crystal system. So our question is no longer different from what we have solved before. Okay. Still, we will do the same. We have two plane. One we can write 111, another is 001. And then here, this is the common direction between them. We'll say that this is UVW. We'll follow the exactly same procedure. We'll multiply them 1 times of U, 1 times of V plus 1 times of W, 111. This would be 0. Here we will get U plus V plus W will be 0. We'll do for this also. Same plane, 001, same. What we will get? 0 times V plus 0 times U plus 1 times of W will be equal to 0. From here we will get W is 0. Right. So W we got 0. Substitute back somewhere. Let's say here we are substituting. What we'll get? W is 0, so we got that U will be equal to minus of V. All we need to find is U, V and W. And we got that. U is what? Minus of V. V we can write V as it is. W is 0. We can reduce them to the smallest possible integer. We'll divide all of them by V. Minus 1, 1, 0. Okay. Again, we'll write the bar at the top. So this is our final answer. So we not followed any different step for triclinic. The way the question was, Weismann law was sufficient to answer this thing. And so we not needed anything from the geometrical perspective. Whenever we see triclinic, it's A is not equal to B not equal to C. And all the angles are also differ from each other. So it will be very complicated. But whether it's to consider as a triclinic or whether it's to consider as a cubic, both are exactly same here. Okay, the way we are solving the problem will not differ. Great. Any doubt in this part? Let me know. If not, let's move ahead to the next part, question number 20. Before 20, I would like to solve question number 21. Just a minute, guys. I think I made some mistake in this question. Yep, will not solve this question. 22, 22 will be fine. Yeah, that's great. 22 is the direction. See, we solved Weisman law, right? This is the next version. The direction that bisect the plane normal of this and this. We need to find the direction which is bisecting the plane normal of this. The important key here is that it's a cubic unit cell. How to solve this? We have a plane normal. Let's say this is a plane number 1, plane A. This is a plane B. Let's say this is a normal of the plane A, and this is a normal of the plane B. And we need to find the direction which is bisecting them. This is our required direction. Let's say UVW. But for that we need this vector, this direction and this direction. Direction of A and direction of B, which is 1, 1, 1 plane we have. Let's say this is the plane 1, 1, 1, and what we need to find is the normal vector of this particular plane. This is where one important feature of this cube come into play. This is only valid for the cube, that H, K, L of this is equivalent to the normal of the H, K, L of the direction. They are equivalent. So whatever is the plane which is given, the normal will also have the same direction. Okay. So 1, 1, 1 will have 1, 1, 1. So this is only valid for the cube. Okay. So this direction is perpendicular to this particular plane, HKL plane, and this direction HKL direction, they are perpendicular with each other. It means that this is a nothing but a normal to this plane. So we got this particular one, that this direction is 1, 1, 1. B direction, again the same thing. Normal to this particular plane will have the direction of this itself. Will have this itself 1, 1, 1 bar. Now what we need to do? We need to find this bisector. Bisector will be exactly in between them. So what we can do? We can add them. 1, 1, 1 plus 1, 1, 1 bar. What we'll get? 2, 2, 0. They will cancel out with each other, and now we can reduce them to the smallest possible integer. So here we got the right answer to be the B. Here, so last question was based on the Weisman law, which was like it is valid for all of the crystal system. But this particular equation, this particular information is only valid for the cube. So any plane, but we add it. Yep, we add it. Okay. Let's go to this part. Let's say we have this direction and we have this direction, and we want to find the bisector of that. In which direction the bisector will lie? So this is A, and this is another thing is B direction, and we have to find this one, C. Let's move the B from here. Let's move B from here and make it to come over this particular one. This is also the B vector. So now we'll do the back. We want to find the C. We know A and B. So we know that we'll go from this direction. A, B is equivalent to the C. So if I want to find the C vector, it will be the addition of the A vector and the B vector, right? So it's a vector addition. If I add A and B, I'll get the C vector, right? So this is why we have added it. If I want to go from here to this particular point, it will be, we just have to follow the another. See, I can rotate in any way. Let's say I'm rotating in this particular direction. Oh, got it. Let me just complete. From here, if I'm going, I'll say C. I will come in this direction again. It will be like, okay, I'm going to the opposite direction of the vector, which is minus of B. Then again, I'm going opposite direction. It will be minus of A. It should be equal to 0. Starting from here, ending here. So C should be equal to A plus B. And that's why we have added them, and we got the bisector, the direction. Okay. So the important feature of the cube is this. Take any random plane, HKL of the cube. The normal will have the same direction. The indices of this particular plane and the indices of this particular one will be the exactly same. So this was something which was specific to the cube, and the Weismann law was something which was like for all of them. It was valid for all of them. Okay, now let's go ahead. Let's go to the next part. Question number, the last question which I saved it. Question number 20. What is the Miller indices of a plane that make intercept this, this, and this with the axis A, B, and C in an orthogonal crystal with a C equal to 2A, 4B? See how we find the, now we have to remember how we find the direction. Sorry, it's a plane. So what we do, first we'll find where it is intercept is there. It is already given. Along the A direction, RM is to find the Miller indices. Along the A direction, the intercept is 1 angstrom. Along the B direction, it is 4 angstrom. Along the C direction, it is 8 angstrom. These are the intercepts. Intercept is given to us. Next step, what we do, let's say we got the intersecting at the 2A, 2, 3B, 4C. What we do, then we remove A, B, and C. What it means that we are dividing it by A, we are dividing it by B, we are dividing it by C, so that we only get the number 2, 3, and 4. So here also what we will do, we will divide them. We will find the fractional coordinate. We are finding the fractional coordinate. Fraction is it is respect to the unit cell, that particular unit cell, that whatever length A, B, and C was having. So 1 angstrom divided by A, 4 angstrom divided by B, 8 angstrom divided by C. Right? Clear? So we got till now. But now also we know the couple of things over here. What we know is that C is equals to the 2 times of A. And okay, sorry, I think I made a mistake over here. C equal to 2B equal to 4A. So C will be equal to the 4 times of A, and B will be equal to the 2 times of A. Let's simplify this and then we'll take the reciprocal of it. Okay, so what we'll get, 1 over A, 4 over 2A, 8 over 4. A we can remove. Here we'll get 1, here we'll get 2 because they will cancel, and here also I will get 2. Right. So what I've got at the end, 1, 2, and 2. Reciprocal of the fractional coordinate. reciprocal of them, 1 over 1, 1 over 2 again, 1 over 2. Now all I have to do is do some multiplication, like denominator I have to do. I will multiply them by 2. I will get the smallest integer. So here I will get 2, 1. So this is how I found 2. So this is the int. What we can say, this is the Miller indices of the particular plane, which was making intercept of the 1, 4 and 8 angstrom. Okay, we follow the same procedure. First we found the intercept. What was the intercept was given. We divided it by the a, b and c, and then after dividing we just normalize, we made it the smallest possible integer, and then we reciprocate, and then we again just took the smallest possible integer. So this is how we have solved this question number 20. Okay, you might get certain question like this in the quiz, maybe not. Okay, so now with that all these questions are over, but I wanted to solve one questions with you, that see, let's say body diagonal in cube. Can someone tell me what will be the body diagonal in the cube, the Miller indices of the body diagonal for the cube? Body diagonal means 1 by 2, 1 by 2, 1 by 2. We can further multiply them. We can remove this 2 and we can make the smallest possible integer, right? Yeah, right, Omkar. It is 1, 1, 1. Now, keeping body diagonal as same, instead of cube, I write tetragonal. What will be the body diagonal for my tetragonal? In the case of cube, A was equal to B, it is equal to the C. In the tetragonal, A is equal to B, but it is not equal to C. I'll go to the next part also, orthorhombic, where A is not equal to B and is not equal to C. How the body diagonal will be in that case? That is 1, 1, 2. Any other answer for the tetragonal one? If I consider C to be the 2L, let's say C is not equal to A, let's say C is equal to the 2 times of A. Now, this is where the crystallography play. The Miller indices are designed in this way only. The right answer for all of them is 1, 1, 1. Okay, don't get confused with the two-way or anything, any number. The body diagonal for the cube will represent by 1, 1, 1. Body diagonal for the tetragonal will also be 1, 1, 1, 1, 1 itself. Okay, this is where we took the reference, remember? A, B and C. So that's where we were dividing all of them, divided by A, divided by B, divided by C. If it was 2A, 2B, 2C, we will still divide it by A, B and C. It doesn't matter to us. This is the one. Why is it? Okay. Now we have to understand that. Very good. Let's draw a cube. Then we'll draw a tetragonal. Then we'll draw a orthorhombic. One of their body diagonal will start from this particular point and will go to over here. When we write the Miller indices 1, 1, 1, What it mean? This was the origin. What is the meaning of this particular mirror indices? It is saying that this direction is nothing but you move by crystallographic amount in the a direction by 1a, 2b and 2 sorry 1a, 1b, 1c. Move by one amount by a, b and c. You will get this particular point. I am moving by a in x direction, in this direction, b in this direction, and then c in this direction. Only one times, right? If it would have told that 2 times c, I will move 2 times also, but it not told. 1 1 1. We are only talking about the 1 1 1. So this direction is representing that okay, you move by the amount of a in this direction, in a direction. In b direction you have to move by b itself, and in c direction you have to move by c itself. Same if I write for the 1 1 1 for the tetragonal. This is my origin and this is my another point. This is the body diagonal. To get to this particular point, we have to move by the A in x direction, by the B in y direction, and by the C in z direction. Here we not specified anything that whether A is equal to B equal to C. This has nothing to do with that. A equal to B or equal to C, or they are not equal, or they all are not equal. All they are saying that move by this much amount in A direction, move by this much amount in B direction, move by this much amount in C direction. This is what they are saying. This is what their meaning is. So even whether it's, I asked, right, that where is the question? Tetragonal, cubic, tetragonal, orthorhombic, even for the triclinic, it will be 1 1 1. So, and this is what we call that Cartesian coordinate system. Sorry, crystallographic coordinate system. In Cartesian coordinate system, what will happen? They will differ. Cartesian coordinate, what it take into account that same amount in x direction, y direction, z direction, they will move by the equal amount, and that unit is fixed. But the way we are moving, our unit is in different direction. It's a different. Here, let's say I cap. We are moving by I cap, j cap, and k cap. The thing is that their magnitude are one itself, only one. Their magnitude are one. They will move. You are moving wherever you are moving. You are moving by this unit. But here our unit is different. Here we are moving by A in x direction. In B direction we are moving by the B, and in C direction we are moving by C. So this is what we call as the crystallographic coordinate system. So now let's change the question. Sir, is all the crystal structure is 1 1 cost? Is all the crystal structure is 1 1 1? I not understood the question, Omkar. Sir, is all the crystal structure is 1 1 1? Question is not clear. Can you specify? You can also unmute and interact with me, no problem. Or you can also write your question in the comment box. Okay. So what I was telling is that the direction is okay. Now someone asked about like at the body centered for the cube, for the tetragonal, and for the triclinic. Okay, I'm saying triclinic because all of them will come into the picture. Now, if I'm telling that I place an atom at the body centered, how will you represent that? You will represent by 1 by 2, 1 by 2, and 1 by 2. Body centered, right? At the center of the body. Tetragonal also 1 by 2, 1 by 2, 1 by 2. Triclinic also 1 by 2, 1 by 2, and 1 by 2. It's just that here the A, B, and C, they all are equal with each other, and here A is equal to the B, but it is not equal to C. But still, that doesn't matter for our crystallographic coordinate system. The way this is the reason why we define the Miller indices and the plane and all for the easiness for us to solve these questions. So if it is sitting at the body centered, it will be 1 by 2, 1 by 2, 1 by 2. The Miller indices will be like this itself. Miller indices is not going to change. Only thing that is going to change will be your A, B and C. C will be, if in cube it was this, it will just stretch. So this is how it's going to be. So any doubt in this, guys, let me know. In this entire discussion that we have made. If not, because our this list of the questions and the thing that which I wanted to solve, it is over. And I'm just telling you, one question is there in the quiz in the assignment I saw, which is based on this the concept which we have discussed. And if you are able to solve, that will be good. Okay, Omkar has replied something. Sir, you have said that the irrespective of the structure for the body center tetragonal. So is it same as 111 for the monoclinic? 111, is it same as 111 for? Actually, 111, are you referring to the plane or you are referring to the direction? That is the thing. What this 111 is represented of? Miller indices plane. See, Miller indices of the plane will remain 111, but what will change is the family. Family will keep on changing. Okay, because you will keep on distorting them in the way. So 111 plane, it has the same meaning what it has in the cubic, tetragonal, orthorhombic, so on in the triclinic. 111 have the same meaning. As you keep on lowering the symmetry, for example cubic 3, then like 3-4 fold, you are going lower symmetry triclinic, your number of family of plane corresponding to the 111 will keep on decreasing. Okay, so those are the lot of the thing that is related with the symmetry part. Okay, so it's good that at this particular stage we are able to think a right question, which is very important. Okay, so from here, the thing that we have mentioned is that whether it's if I'm telling the body centered, so irrespective of the crystal system, the body center will be 1 by 2, 1 by 2, 1 by 2 only. It's just that 1 by 2 of A, 1 by 2 of B, 1 by 2 of C, that is we have to keep in our mind. But the Miller indices will be represented by this itself. Okay, this is the Miller indices, you can say, of that particular coordinate. Okay, so this is the entire thing, and there is one question based upon this particular concept that we have discussed. Question will try to confuse you, giving certain additional information, but you have to be safe from that. Okay, any other doubt guys for the week 2 or anything that we have discussed? If not, then we can wind up today's session. Oh, it went more than the last time. 4:54 it is. Great. Okay, then we can wind up today's session. And sorry, one more thing was that next week Saturday I am occupied. So Friday will be the fine or Sunday will be the fine. Timing will be 3 to 5 only. Whatever you guys say, I'll keep the session on that. Either the Friday or the Sunday, because next week Saturday I am occupied. So what you guys prefer? Sunday. Omkar is saying Sunday. So everyone is fine with the Sunday? Okay, great. Then next session will be 3 to 5 Sunday. An announcement will be made according to that. Okay. So our timing is fixed now. Next week we'll go for the Sunday 3 to 5. Okay guys, bye bye. With that we are ending our session.